Hey everyone. Okay, let's see what kind of answers you get for Tool 8 here, right? How using parallax and finding distance. So, the first page has some questions, but we're doing this in order. So, here we go. Right. Doing this in order, right? If we're measuring the parallax angle, right, from Earth to this star, then, in January, Earth sees this star over here, right? In July, Earth sees the star over here, shifted over here, and therefore its full angular shift is like this, or like this. They're the same angle, right? Over the course of the year, but then you don't take the full angular shift, you divide by 2 to get the parallax angle, right? In order to figure out this distance. And if you pick a star farther away, and I haven't drawn these lines yet, right? If you pick this star here, I'll put it there, all right? Let's say you got a star farther away, like this one here, right? Well, then in January, that star appears in front of this star here, right? And then over the course of 6 months, in July, that star appears to be over here. So then, got a little bit out of alignment, but I'll draw this. Getting a little messy here, right? So now this, that's ugly. Now that's the parallax angle for this other star. Right? Now, which star has the larger parallax angle? This angle certainly looks larger than that one. So why does this star have the larger parallax angle? Because it's closer to us. Right? The star that's farther away is going to make a longer, skinnier triangle, and so that parallax angle as seen from Earth is going to be smaller. Right? So, going back to these questions on the first page here, right? How do the parallax angles compare? Well, the farther away star has a smaller parallax angle. Will the more distant star have a larger or smaller parallax angle? It'll have a smaller one. Are the distances to stars directly proportional or inversely proportional? Well, what does that mean, right? If two things are directly proportional, if two properties are directly proportional, then that means that as one increases, the other one increases, right? That would mean that as the distance increases, the parallax increases. And if the distance decreases, then the parallax decreases. Right? Two properties are inversely related. I won't say inverted, right? They're inversely proportional if, as the distance increases, the parallax decreases. Right? So, for stars, as the stars get farther away, do their parallax angles get bigger? Or as the stars get farther away, do their parallax angles get smaller? Well, based on our drawing here, as the stars get farther away, the parallax angles get smaller. So therefore, they must be inversely proportional. Right. Okay. Then you looked at these star fields here and found the star that is moving, right? This is how it really works, right? This is giving you a bit of the wrong view of what we really do here on Earth, right? Because, we're not getting above the solar system and looking down at Earth, right? We're standing on Earth, watching these stars and seeing how those stars shift, right? This way from here to here, or from here to here, over the course of a year, relative to these background stars, right? Why are there these background stars? Well, these background stars here are the stars that are so far away that their parallax angles are unresolvably small, right? Are these stars not moving? Do these stars not have parallax? Well, they do, right? Because the Earth is revolving around the sun, right? So all stars have a parallax angle, and the farther away the star is, the smaller its parallax angle is going to be. So all of these stars, these are the quote-unquote background stars, because these are the stars in the sky that are farther away than your telescope can resolve. They're so far away that they look like they're standing still. And therefore, those stars make good fixed points that you can use to find the stars that are moving, or that do appear to move with parallax, right? All of these stars aren't moving. Why? Because their parallax shifts. If this star is moving back and forth with parallax, it's moving so little that in your telescope it looks like it's standing still. Right? We can't resolve the tiny little parallax shift for those stars. This one, however, is the one in the foreground, right? This star, however, is the one close enough that we can see the parallax. And so it shifts over here from February to March to April. From January to February to March, it shifts over here, and then it gets all the way over here, and then it starts moving left, 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 come back to July, and it's moving left, left, left. It's getting as far to the left as it can go, and then it starts moving right, right, right. And then after December, where does it end up? Well, it ends up in the same place that it was the previous January. Right? It makes one shift over here, to over here, to over here, and back in 1 year. Not because the star's moving, but because the Earth moves around the sun in 1 year. All right? So, this is what we really do as an astronomer. This is what we do, is take a picture of a field of stars, and then come back a month later, and then a month later, and a month later, and a month later, and see which stars move. Right? The Gaia spacecraft takes a map of the sky. It maps out the sky over and over and over and over again to find the stars that move from month to month. So, if we look at this, right, here's our same star field, but the star whose parallax we can see, it's not on here. So we're going to say, all right, the star starts over here, it shifts over here, then it goes over there, and then it comes back 1 year later. Right? Well, how big is this? How big is this shift from over here to over here? Well, we know that a line this big is 0.25 arc seconds. Right? How do we know that? Well, because you know your telescope and you know your camera, right? When you know your equipment, you know what the magnification is on the image, you know what the field of view is on your image. And so this is obviously not a picture taken with a telescope, this is a cartoon, but you would know, okay, given that I know the equipment that I used, anything this big, anything this long in my image, that angle is a quarter of an arc second on the sky. Well, how big is this line compared to this line? It's about 4 times, right? It's about 4 times longer. So if this is a quarter of an arc second, what is the angle of this full shift? Well, if this is 4 times longer than that, then this full shift must be 1 arc second. Is that the parallax angle, though? No. Because, remember, the full angular shift, right? The full angular shift back and forth, if that's 1 arc second, you divide that by 2, right? The parallax angle will be half of that shift. And so the parallax angle for this star, if this full shift is 1 arc second, the parallax angle must be half an arc second. Okay? And so that means, where's the question? Right? That means, how far away is this star? Well, if the distance is 1 over the parallax angle, right? And in this equation, you always put the parallax in arc seconds and you get the distance in parsecs, then that means this star has a distance of 1 divided by 1/2 arc second. Right? What is 1 divided by 1/2? It's 2. So that star has a distance of 2 what? Well, this equation gives you the distance in parsecs. So that star must be 2 parsecs away. Now we know how far that star is. Right? These other stars must be much, 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 much farther away than 2 parsecs because their parallax angles are so small we can't see them. This is how we do it in reality. This is how in astronomy you watch the stars shift back and forth, you measure that angle, plug it into the equation, you get the distance. All right? Okay. So let's look at these practice problems. Right? I'll move this up here and make a little room because, hey, if I'm going to do this over and over again, right? If I'm going to take the parallaxes for these stars and calculate their distances, I don't want to have to do that on my calculator over and over again when I've got my spreadsheet to do this for me. So, all right. Mirfac has a parallax of 0.0055 arc seconds. So what's its distance? There we go. 181.8 parsecs, or 592.7 light years. 181.8 parsecs, or 592.7 light years. All right. Almach has a parallax of 0.0093 arc seconds, so it's got a distance of 107.5 parsecs, or 350.5 light years. Kochab, only 40 parsecs, and 130.4 light years. And Regulus, 0.0423, 23.6 parsecs, or 77.1 light years. Okay, so what is the relationship between parallax and distance? Well, which of these stars has the greatest parallax? Which one of these is the largest number? 0.04. Right? So Regulus has the largest parallax. Which one has the smallest parallax? Mirfac does, right? Mirfac has the smallest parallax. Which star has the greatest distance? Mirfac does. Which star has the smallest distance? Regulus does. So closer stars, right? The stars that are closer to us with the smallest distance, they have the largest parallaxes. Distant stars don't have larger parallaxes. The distant stars have the smaller parallaxes. Okay. So since I already started my spreadsheet to do the math for me, that saved me a lot of time. All right. And hopefully it did the same for you. All right. With that under our belts, we can move on to the other things that we can discover about stars now that we know how far away they are. All right. Have a good one, everybody.